Oh, welcome, Joachim Moeyens, to the Quantum Feedback Loop podcast, and welcome back, Alec Koumjian. It's been, I think, about two and a half years since we spoke. So, really interested today in discovering more about asteroid defense and the work that both of you have been doing on it from different angles, I guess. So welcome.
Thank you.
Yeah.
Yeah, thanks. Glad to be back.
Yeah. So maybe if you could just each introduce yourselves. Maybe we'll start with Alec and just describe your role briefly, and then we'll go to Joachim.
Sure. My name is Alec Koumjian. I joined Asteroid Institute, part of the B612 Foundation, about 3 years ago, and I head up the software engineering team there. Where so I primarily kind of drive our engineering roadmap and to some degree the research as well, and you try to enable our small team of engineers to do as much good work in that arena as possible. My background is in software engineering as a whole, and I kind of came into the work around astronomy and astrodynamics. It's certainly been an interest in the past, but I didn't really come into it professionally until I joined this organization then.
That's great, thank you. And Joachim.
Yeah, hi, I'm Joachim Moeyens. I'm a research scientist with the Asteroid Institute. I'm currently based at the University of Washington, where I'm technically a research software engineer. It's also where I did my PhD, and I started working kind of as an intern with Asteroid Institute folks when I was in grad school. And towards the tail end of my PhD, Asteroid Institute actually stepped in and funded the latter components of that work, including the building of the THOR algorithm. And so I've been kind of thinking about asteroid discovery from pretty much the beginning of grad school till now as a research scientist here with the Asteroid Institute.
That's great, thank you. Well, maybe Alec, if you could just start by telling us a little bit about the Asteroid Institute and the B612 Foundation and the work that you've done, and I guess maybe just highlight the achievements, I guess, since we spoke 2.5 years ago.
Sure. So B612 Foundation was started by Rusty Schweikart and Ed Liu with the primary focus on preventing asteroid impacts against Earth. And a major component of that is, of course, discovering asteroids, knowing where they are, being able to track them. And so a number of years ago, the Asteroid Institute was started as a way to enable that work through research and software. And so, in terms of the work that we've been doing, at least since I've joined and since the kind of 2 years since we last talked, we've been doing a lot of things. So one thing we've been doing is building out a whole suite of astrodynamics and astronomy related software engineering tools. So these are largely both open source packages that people can install and use, and as well as hosted services. I'm thinking quite a few of these are new since we last talked. So we have tools to calculate impact probabilities for known or recently discovered objects, along with visualization tools. We even include some services for being able to plan out simple trajectories between any two objects in the solar system. So you could, if you were kind of, for those of you who might be into things like Kerbal Space Program or even actual professionals out there, you can explore some kind of rudimentary, mission designing tools as well. And then a lot of what we do is collecting data and running algorithms against that data in order to do asteroid discovery, and that is primarily the area that Joachim's working in. But we now have over 9 billion individual point source detections from different telescopes. Actually, that's gone quite a bit up, but I haven't tallied it recently. And then we've also accelerated kind of the amount of calculations that we're able to perform significantly since we last talked.
That's great. And I think when we last talked, the main kind of platform was called Atom. And then we talked about the THOR algorithm, which I think Joachim had some direct involvement with. Maybe if you could just explain those two generally, and we can get into more detail a little bit later, but just the general idea behind Adam and Thor.
Well, I can start with Adam, but then I'll hand it off to Joachim for Thor. So the idea with Adam is that it is a platform for doing asteroid discovery and asteroid-related astrodynamics work, and so that folds in, astronomy data and things like that. So what we have there is a host of services, many of which are public, and we let anybody create accounts on Adam on our b612.ai website, and they can use those services. We have some data sets, such as we have an entire replication of the minor planet centers data. We have packaged up spice kernels. We have recent data from the Rubin Observatory as well. And then so Adam is kind of a one-stop shop for doing all of those things, in addition to be paired with those open source tools that I mentioned.
Well, that's great. And you mentioned the Minor Planet Center, which I gather is kind of like a clearinghouse of where all of these observations go.
That's it exactly. So,
Right.
So when people discover asteroids or observations that are related to asteroids, even if they haven't been designated yet, they submit those detections to the Minor Planet Center. The Minor Planet Center does a great job of trying to link those together when they can, and basically they are the official location for designating when an object is discovered. Also, it's the first place you report to when you have, say, a potentially near Earth object as well. And then from there, it gets pulled into places like JPL and NeoCC and other places where they analyze that new data coming in.
That's great. And then you mentioned Rubin as well, the Vera Rubin Observatory. And so maybe I'll go to Joachim for this and just maybe explain a little bit about, because I think you had some involvement with the Rubin Observatory, a little bit about the kind of data that it's producing and whether that data is being used in THOR.
Yeah, absolutely. So the Vera C Rubin Observatory is a telescope that's now been built. It's down in Chile. And they're currently in a kind of a pre-operations phase pre-survey phase where at some point in the near future, the Vera C Rubin Observatory is going to conduct a legacy survey of space and time, which will be essentially this monumental effort to create a 10-year movie of the night sky. And so they're working towards getting that started, but we've already seen some of the early discoveries coming out from the Vera C Rubin Observatory. And so I believe the latest numbers, there's like maybe about 28,000 or so discovery candidates that they've already submitted to the Minor Planet Center, which is an enormous volume, even in just kind of this pre-survey phase that they're currently in. What makes the Vera Rubin Observatory so interesting is that it's an 8-meter piece of glass, and you attach to that piece of glass the world's biggest digital camera. And you let that camera essentially keep taking pictures over 10 years. And so the latest estimates in terms of the discovery yield for the number of asteroids puts it, discovering about 4 million or so main belt asteroids. And for reference, right now we know of a total of 1.5 million asteroids across all different populations. So it'll actually increase the resolution with which we can see the solar system by a factor of a few. And for the objects that get close to us, we're anticipating a factor of a few increase as well. So we know of about 40,000 or so near Earth objects. By the end of LCT's 10 years, that number is meant to go above 100,000. So that's why we're also excited about this particular data set. And what we're doing with Asteroid Institute is we're actually going to be able to use THOR on Vera C Rubin data through Adam, where we are actively going to be ingesting the detections, and we'll be able to find any additional asteroids that were not picked up by the traditional algorithms.
Okay. And so THOR is an algorithm that is looking primarily to detect asteroids or near-Earth objects. What kind of makes it unique?
Yeah, sure. So maybe to start off, so I'm lucky in that I'm both a developer of Adam, but also a user of Adam. And one of the things about ATOM is it's like a collection of all these the different astronomical data sets. And then on top of that data, we build all these really cool algorithms to leverage the science from that data. And THOR is just one of those algorithms. And what makes THOR unique is that it's really designed to find asteroids in data sets that were not necessarily designed for asteroid discovery. And we can probably talk about this a little bit later on about what the characteristics are of an asteroid discovery data set. But basically, THOR is capable of finding asteroids through detections spanning from many, many telescopes without really predefined observing patterns. And so really, ATOM is the ideal place for such an algorithm to run because we can leverage all of the different data sets from different telescopes to find as many objects as possible.
That's fascinating. And in terms of the collaborations, in terms of other institutions collaborating with the Asteroid Institute, B612, University of Washington, how widespread is this collaboration?
Sure. We work with a number of institutions, both kind of officially and just kind of collegially as well. So, for instance, Google, we work in partnership with them a lot. They provide both a lot of guidance and in-kind contribution to make a lot of our work possible. They have access to a lot of computational power, which is one of the things that we need. Just this past week, we've been having fun spinning up some of the GPUs that they have available to do some testing on those. Additionally, I mean, so we depend very heavily on all these various institutions, these great surveys, collecting all this great data. So everything from Noir Lab, which hosts the Noir Lab source catalog, which is where we ran THOR and discovered tens of thousands of asteroids in primarily the dark energy camera data. And then of course Rubin Observatory and all the great work that that organization is doing, as well as surveys like Atlas. So Atlas is an incredible survey with multiple telescopes, and they are give us generous access to their data to be able to pull that down as well. But yeah.
And I wanted to maybe just address the science and the risk and the public interest in this. I know there was a survey, Pew Research Center in 2023 did a survey of 10,000 American adults who said that asteroid defense was actually the #1 priority in terms of space exploration. I think we've seen some events. I think probably the Chelyabinsk meteor, I think it was back in 2011, that hit just outside the city of Chelyabinsk in Russia and could have caused incredible damage. Just, I guess, in terms of what was the inspiration for Rusty Schweikart to start this in terms of selecting it as a priority in terms of what we should be doing with space? And then what are the kinds of things that you're looking for? What types of objects are you looking for? What kind of risks are you looking for? And maybe some of the challenges in finding those objects and predicting where they're going to go?
Yeah, I can. I'll start off with an answer, and I think I'll have Alec chime in as well. Planetary defense, it's an issue that you just have to kind of address. And the longer humanity survives on Earth, the more likely you're going to have a scenario where we might have to deflect an asteroid to save lives, essentially. The Earth is pummeled every day by things in space. They all end up being very small, but every now and then they can be a lot larger and cause all kinds of devastation. And so, like Chelyabinsk from a little over 10 years ago, that was about a 20-meter sized object. There's many hundreds of thousands of those that we anticipate to be out there, and that particular one shattered a few thousand windows. Of course, there's the famous the famous impactor that wiped out the dinosaurs 66 million years ago. So clearly these impacts happen. And so I think if we want to survive long term, we need to know how to do something about it. I think that was kind of the driving motivation for the creation of this kind of institute, but also just broadly the field of planetary defense, which starts with the people at the telescopes making the discoveries and observations, all the way down to the people on the ground who would be responding to these kinds of events. And so I think what at least what I'm focusing on now with the Astro Institute is we have a discovery algorithm called THOR, and we want to basically extend this discovery algorithm to work on finding those impacting asteroids. And what makes them difficult to find, or just asteroids in general difficult to find, is that they tend to be pretty dark, and so they're very hard to see. We also kind of rely on angles only observations where we can see where on the sky they are, but we don't know the distance to them, and that adds quite a lot of uncertainty to their orbits. And so it's really, we need to, basically what we have to do is we have to get as many observations as possible of these objects so we can understand what their trajectories to the solar system looks like, and then also then map where the Earth sits relative to their trajectory, to essentially be able to say, like, to be able to rule these objects out as an impact, but also if they might be an impactor, actually figure out when they're going to impact and what kind of mitigation strategies we would have to deploy to be able to prevent that impact, basically.
Mm-hmm. And I think it was a few years ago, the DART mission, NASA's DART mission, was sent up to try to deflect a rock in space, and it actually worked. So I think there is that hope now that people have, that once we detect something, we might actually be able to do something about it.
Just to chime in, so DART was a phenomenal example because that was a mission that I think launched in 2021 and then actually hit the moon of an asteroid in 2022. And, if I remember correctly, their success criterion was if it changed the orbital period of that asteroid around its moon by roughly a minute, and it ended up changing it by 32 minutes. And so just it's a beautiful demonstration of what we are able to achieve if we know about an asteroid potentially, impacting the Earth. Of course, this moon was no threat to the Earth, but it was basically a demonstration of what we could do to essentially prevent an impact. So yeah, and I think that mission was also one of the driving functions to seeing more interest in planetary defense as well, going back to your earlier question.
Mm-hmm. And Alec, I wanted to get your thoughts on, I think it was in 2024 that there was an asteroid detected that had, I think at one point, a 3% chance of hitting Earth. And maybe if you could just tell us a little bit about the method of calculating those percentages. I mean, that one made headlines. Mm-hmm. Is there, how much variability is there in it? Like when we say 3%, right. How much could it differ? Could it be 10%? Could it be 0?
Right. Yeah, that's a great question. It really comes down fundamentally to how we understand where any objects in the solar system are and the limitations of those methods, right? So 2024 YR4 was discovered in those systems that I described earlier, where observations are submitted to the Minor Planet Center. They go to pipelines like the NEO confirmation page. JPL has like a dashboard called Sentry. There's one at that ESA has as well. And so it starts off, it goes through all these algorithmic pipelines. They have a method for calculating that impact probability. And then over time, as follow-up observations are added, those probabilities change. And the way that happens can be a little bit counterintuitive if you're not familiar with the process. But really, it starts with the observations. So as you're taking in those observations from one or more different telescopes, they have uncertainty built into it, right? Because we don't, there's uncertainty in exactly how exactly what point in the sky it was. There's some unknown into exactly how precise you can be, even to the clock that is associated with when that image was taken. And that's just the uncertainty in the observations. Then you have to fit an orbit to it. And when you fit an orbit to it, you're essentially saying what can go through all these detections at the times and locations that they were taken, that kind of also follows the physical laws, the gravitational laws to drive it in that direction. And you have to basically refine that and infer how far away it was at different times and the velocity at which it's moving, things like that. And so when you do that orbit fitting off of those detections, you don't just get you don't just get a point ellipse going around the sun. Instead, what you get is more like a probabilistic cloud that has often we describe it as a bananoid shape. It's kind of like long and tubular generally, and so I'm glad Nakam's yachting because he's more the astrodynamics expert than me. But so given that we have, when we do that orbit fitting, we get this cloud, and you're trying to essentially project that cloud through time and see if it's going to be at the same point in time as the Earth is in the future. And so essentially, you can kind of think of it as the accumulated amount that probabilistic cloud overlaps with where the Earth is going to be at a given point in time. That represents your impact probability. And so 2024 is a great example here because you start with some potential impact and some amount of uncertainty. And as that uncertainty shrinks because you've gotten more observations, your impact probability can increase just from the sheer fact that the percentage of the impacting region is now a larger percentage of the whole uncertainty region. If that, you can kind of think of it as like overlapping circles. When the bigger circle gets smaller, if the smaller circle that represents the Earth is still in there, now it has an increased percentage. Now what happens is if it's not going to hit the Earth, as that uncertainty region shrinks, it can essentially shrink off of where the Earth is going to be, and you suddenly go from an increased impact chance to a zero or negligible impact chance. And that's what happened with 2024 YR4, and we're likely to see it again a lot in the upcoming years as well.
A little bit frightening, I guess, to think that, 3% seems like a small number in some senses, but it's a lot higher than anybody would like it to be in terms of protecting the Earth. So now the Chelyabinsk meteor just came out of kind of nowhere, right? There was no prediction of that one, I think. And is that scenario still possible?
Yeah, I think so. Chelyabinsk came at the Earth from the sunward direction. So most optical telescopes, they're observing at night, and so they would not. It was basically not detected until it impacted. Chelyabinsk is a really interesting example for me because the same day another asteroid also had a close approach with Earth, and that asteroid was called Duende and flew within geostationary satellite distance of the Earth. Just a little tidbit there, which I always really appreciate. But so that's, you're actually addressing a really fundamental issue kind of with the whole planetary defense architecture, is that most telescopes that are the prolific discoverers of asteroids are limited to observing during the night. And so that's why you get ideas like the NEO Surveyor telescope, which is meant to be launching, I think, 2027, maybe 2028, which will be essentially parked between the Earth and the Sun, looking in the sunward direction, kind of along Earth's orbit, to try to find those asteroids that the optical kind of nighttime observing telescopes are more likely to miss. And so that's, again, an idea of, we want to have as many eyes on the sky as possible, looking at all the regions where these asteroids can come from to prevent a Chelyabinsk-like example. Yeah.
Yeah, and so it's interesting that you mentioned the sunlight being a big factor, I guess, in this. And it reminds me, I guess it was in 2024 that we interviewed Joe DiMartini, the first recipient of the Schweikart Prize given by the B612 Foundation, who was proposing that the Rubin Observatory could look in the twilight hours for these objects. So I guess that just is another example of how the possibility of detections increases, and you can connect more of the dots and presumably calculate the risks even better.
Yeah, absolutely. So like at twilight hours, so from Earth we can see Venus, and Venus is interior to Earth's orbit. And so if you're able to tell your telescope to observe at near twilight hours, you're actually able to probe inward to the Earth's orbit as well. And so that's one of the reasons that he won the prize for that award, because that would actually really help with planetary defense.
Yeah, and Alec, I wanted to ask about, you mentioned time, the difficulty in projecting time, both for the object's trajectory, but also where the Earth is going to be at the same time. And I think this relates to the precovery mechanism, I think, that you spoke about a couple of years ago on the podcast. And so I just wanted to ask you about that precovery, and if that helps to remove the time dimension from the problem.
Well, precovery helps in that fundamentally it's a tool to just gather more observations for an object for which you already have a some kind of orbit fit. So the idea is you have some orbit and you want to say across all these billions of detections and hundreds of thousands of unique exposures, which ones are likely associated with this object. And you might think, well, if you can associate it and you can find it, then how does that really help? Because you already expected it to be there. But basically what you're doing is, again, you're kind of taking that, it could be in some wider range of areas. And by finding additional detections farther out in time, you are constraining that uncertainty potentially quite a bit. And so recovery we are still working very hard on it. Actually, we have something in the works, some major improvements for both performance and the scale of recovery. And it works very much in tandem with kind of how THOR works in terms of being completionist and trying to recover as many detections for an object as we possibly can.
Mm-hmm. And so do the detection devices have to be correlated in time? Like if you are you able to take detections from several different devices that are taking the images at different times? Is that one of the problems in terms of correlating the data?
So recovery is agnostic to the basically to the observer as we think of it. So just like THOR is more or less agnostic to the particular telescope and the observer. Similarly, the way we've written our recovery algorithm is more or less agnostic. And so what that means is that we can take that survey data that we're taking in from Atlas. We have some trickling in from the Rubin Observatory, from ZTF, from NOIR Lab, and we can use all those in the same algorithm because we essentially position it to very accurately. We can project where those objects are going to be from the perspective of all those different observatories at the time that they took their exposures.
I see. Okay.
I don't know if Joachim has anything to add on that. Sorry.
Yeah. I was actually just going to ask Joachim if you could, add to that maybe, but also then maybe take us a little bit into THOR and exactly how it works and what it does.
Yeah, sure. So recovery is a fantastic tool. That's a great tool that I really enjoy using. And the way that I think about recovery is, so there's this idea of follow-up, right? So say that the community discovers an asteroid, and we need to understand its trajectory a lot better. And so the thing you might do is you say, oh, here's all these telescopes. Let's task those telescopes to see if we can find more observations and actually take more observations of that asteroid. Recovery is basically a much cheaper way to do follow-up, where you say, oh, we've already discovered an asteroid, but we have all this data where there could be detections of that asteroid in that data. And so it's basically the cheapest form of follow-up, where we look through older detections and say, oh, this potential observation made by this telescope a few weeks prior to the discovery of this asteroid could actually belong to that asteroid. And then suddenly we get this automatic arc extension that then improves the orbit fit. There's obviously going to be limits to how far we can extend them, because if we have only a few days of data, that orbit's not going to be very valid many weeks from that initial set of data, because the uncertainty region gets so large. But so basically, Precovery is a really, really powerful follow-up tool where we, again, in the theme of Atom, try to leverage as much from our data as possible. And then to your question about THOR, so I think the best way to understand THOR is to kind of understand how asteroids are typically discovered, and then to kind of discuss what THOR does differently. And so an asteroid, if you take a single image of the night sky, and you were to just look at all the point sources of light, you actually can't tell an asteroid and a star apart. That's where asteroids derive their name from. That means star-like. And so the discovery strategy for the last several decades has always been: you take an image of the night sky, you then come back about 30 to 90 minutes later, you take another image, and then you come back again to that same area of the night sky and take another image. And basically, in that sequence of images, all the stars will stay in the same position, but an asteroid will start shifting a little bit. And so when Atlas does this kind of observing pattern, or when the Pan-STARRS telescopes do this, they basically take the measurement of those three or four detections moving and submit those to the Minor Planet Center. And then the Minor Planet Center says, oh, look, Pan-STARRS saw something moving in this direction over here. Atlas saw something also moving in this direction over there. This could be the same object. And so that's kind of the status quo today. The Vera C Rubin Observatory is going to do something different, where basically the Vera C Rubin Observatory is going to say, because the telescope is that the mirror is so large, the camera is so large, they're going to have so many detections that they can't really send all their tracklets, all those measurements of that motion, to the Minor Planet Center. So what the Vera C Rubin Observatory is going to do is it's going to observe the night sky, take that pair of images, come back again 3 nights later to the same field, take another set of images, then again 3 nights later, take another set of images, and then try to link those tracklets across nights, and then submit those to the Minor Planet Center. And what's kind of interesting about both those setups, whether it's Atlas, Pan-STARRS, or Catalina versus the Vera C Rubin Observatory, you basically need multiple images in a single night to be able to discover asteroids, right? Because you need to be able to observe the motion of an asteroid. And that's what the inspiration for THOR was. And so when I was in grad school, my PhD advisor at the time, Mara Juric, basically pulled me into his office and started drawing like a diagram on his whiteboard, where we were talking like, how could we build an algorithm where you don't need to make repeat observations within a single night, and instead see if we can link individual detections across nights. And so that was in 2018 that we started looking at this, and then we basically built out a discovery algorithm that removes that requirement. And one of the subtle consequences of that is, if you now no longer need those tracklets to discover asteroids, you are now actually able to look for asteroids in many, many more data sets. Because a lot of astronomical data sets from telescopes were not designed with that observing pattern because they weren't looking for asteroids. And so that's kind of the thing that makes THOR unique, is that it just gives us the ability to look for more asteroids in more data sets. Now, this all sounds too good to be true, and that's largely because THOR requires a lot of compute power, an enormous amount of compute power. And that's why we need a platform like Atom that sits on Google Cloud, where we can throw tens of thousands of machines at the problem to try to discover as many asteroids as possible.
So as you described the tracklets, the process of taking images every 3 nights to plot the movement of these star-like objects, how does THOR dispense with that need to you mentioned that you don't need to follow the tracklets anymore.
Yeah. So basically, from the Earth, so observing from the Earth is kind of problematic because the Earth is also moving quite a bit. And so if you imagine you could sit on the sun and watch your asteroids move, they would essentially move in like these circles around you. And that motion is a lot easier to model than it is and it's also a lot more computationally efficient to model. And so if you're able to somehow convert your detections from a telescope that sits on Earth to essentially looking like it was made by telescopes sitting on the sun, you'd actually be able to make finding those asteroids a lot easier. And that's what THOR is doing underneath. We basically transform all of the detections that we have to make it look as if the telescope was tracking the motion of an asteroid. It's kind of like the same. I mean, this might not be the best analogy, but I kind of think about sitting in the middle of a racetrack and you have a bunch of cars going around. And if you wanted to be able to say, like, what is the speed of one car relative to the other, or say what direction they're going, if you're just taking images looking at one area of the track, you're just seeing cars fly by, right? But if you now follow one of the cars and start taking images, that car sits in the middle of your series of images, but you see all the other cars move relative to that car. And that's kind of the way that THOR works. We basically change all of our observations through a series of transformations and all that kind of stuff to make it look as if that telescope was tracking the motion of an asteroid. And so basically we are creating our tracklets not over the course of a night, but over the course of many, many nights by finding individual detections, by doing that kind of that transformation game, so to speak. And so that's kind of the secret sauce. Yeah.
Mm. So making those connections to kind of get a sense, I guess, of the orbit. I guess when you were talking about sitting in the middle of the racetrack, you have all of these things orbiting around you, not just one single point.
Exactly.
How many?
Yeah.
Yeah. How many asteroids has THOR helped to discover or discovered directly?
Yeah, that's a great question. So a few years ago, we announced about 27,000 or so high quality discovery candidates that we extracted. We've submitted roughly, I think, 15 to 16,000 of those to the Minor Planet Center. And a lot of those have now gone on and have actually like been designated. So that puts them in the preliminary discovery category. And it's not until I think it requires like 6 years of observations before they officially become a numbered object. But we are actively working on making THOR. So because THOR is doing something very unconventional, there's a lot of work that we have to do on our side to make sure that the objects that we identify have the correct attributes, that they're as high quality as possible. And right now, our focus has really been on the main belt, and so we're working our way inwards to the NEO population, and so that's where really the majority of the work has been. And so some of the candidates that we wanted to submit were also NEOs, but we are now going through and also making sure that we can continuously improve the algorithm, so we keep submitting as high quality of data as possible, and so also that we can keep pushing the frontier for that kind of discovery.
Hmm. And the NEO, the near Earth objects, I was curious, where's the dividing line in terms of near Earth and not near Earth?
Yeah, that's a great question. NEOs is a funny name because the technical definition is any object that comes within 1.3 AU of the sun. And so, that can be a Mars crossing asteroid that crosses the orbit of Mars and then makes its way inward. It can also be like an Oort cloud comet that just happens to get very close to the sun. And so NEOs are really just anything that at some point in time during its orbit might be in the vicinity of the Earth. Majority of NEOs do not pose any threat, but a subset, as we know, might, right?
Okay, so it's potential to come near Earth. It's not necessarily that it is near Earth at this moment.
Correct. Yes.
Okay.
Yeah.
So I mean, there was the Apophis, I guess, was the big one back. I don't know how long back that was, a dozen years ago or something, but it was thought to have a risk of hitting Earth. So it was, I guess, even though it's far away, it was considered a near Earth object. Maybe it still is. I think is it projected to come between Earth and the Moon?
Yeah. So I think it's like middle of April of 2029. Apophis will be going through a close approach with the Earth. It'll be about 30,000 kilometers off the Earth's surface. So that's well within that's actually within the orbit of certain satellites. So it's very, very, very close, and it'll actually be visible to the naked eye for a lot of that close approach. But so Apophis is still an NEO. It just orbits in the Earth vicinity, and on occasion it gets close. And so in 2029 is the next time it will get close.
Mm. Yeah, and obviously we want to make sure we do everything to detect all of these potential close things. Alec, I'm just wondering, I guess since your involvement started with the Asteroid Foundation or the Asteroid Institute, how has the scientific community sort of responded to the increased ability to detect asteroids? And in terms of the B612 Foundation and the Asteroid Institute's work, how has that changed things? Has it had a major change over the past few years in terms of the increased ability for detection?
So I think there's a lot going on that's been happening. So I've definitely seen it. It's I'll say this. It is actually a kind of a small world, so to speak. The people studying these things, both in terms of objects which might pose a risk, but also just kind of minor planets in general. And so what I've seen with the things that we've been building, we have a number of very active users of services like Recovery to try to find those additional observations to submit, both for all sorts of interesting objects, not just NEOs. We've seen I think there's been a lot of anticipation around the data that is going to be coming from the Rubin Observatory. And so we have kind of this trickle of data coming in, but we and others have plans to kind of really scrutinize and get as much good science of it as we can. And also, I'll just say that I think there's kind of there's more people than there used to be interested in kind of looking at these problems. And, I like to think that we are one of the people providing tools and resources for people to both like understand and do good work in this arena. So that includes things like, with 2024 YR4, we built a whole new impact probability suite out of that so that people can, as like a third party that's not part of a government agency and with totally open source code, people can vet the way that those impact probabilities are calculated, and then a whole suite of visualization tools on top of that. I'd also just say that right now things in software engineering are kind of exploding with the advent of AI and other things, and so we are also trying to take advantage of that as much as possible in the most responsible way possible.
Yeah, I was going to ask about AI, I guess, in terms of its ability to make so many more correlations, I guess, that through machine learning processes like that. And I guess with all of this data coming from Rubin, or expected to come from Rubin, I guess there'll be a lot more correlations to make and a lot more computing power, I guess, required. So do you have the computing power, or is that a big problem that's being worked on in terms of combining resources to get that computing power for the Rubin data?
So the answer is both. Do we have the computing power? Yes and no. So in the sense that, especially with the way that we use THOR and the way that THOR works, you can kind of think of it as being given access to a slider or something in which you can kind of turn up the knob and say, how much more compute do I want to use to discover that many more objects? Additionally, because, and Joachim would have more to say on this, because we are trying to really build out the capabilities to discover these NEOs, and that is an even more computationally intensive process, essentially because of things like viewing geometry and the number of possibilities that you have to explore. And so while machine learning and things that explore like multi-dimensional space, can potentially be useful in some of those arenas, part of the ways it's been useful for us is just in making it easier to explore certain ideas faster, even if the software that it produces is still just traditional software that we're reviewing and having unit tests for and all that stuff. So we are trying to get the amount of computation required in order to discover these NEOs down to what we would call like a tractable amount, which is basically actually possible to compute in a reasonable amount of time.
Right. And as you said, I guess it allows you to choose where you want to focus that computing power as opposed to just applying it broadly everywhere. Yeah.
That's
Um, yeah. So in terms of the public concern that I mentioned from that 2023 poll, where 60% of the Americans said that uh, asteroid discovery should be the number one priority for space exploration. That's probably still around. I guess we don't hear too much about asteroid discovery in the media. I guess there's just so much other horrible news going on that the good work of people who are working on planetary defense doesn't really come out in the headlines necessarily these days. And I was just wondering, for people watching or listening to this, what what's the message to them? How can they get involved? How can they do something to further this mission?
Yeah, I can take a quick stab at that. That's a huge question, so I appreciate that. Honestly, I think about it in two ways. The first one is, you have to start the earlier you start solving problems, the better. And so a big part of that is just being aware that this is a potential risk and understanding what that looks like. And so, just showing interest and talking to other people about it, I think is just the number one thing that you can do. And one thing I find so interesting is, when I meet somebody new and I tell them I work on asteroid discovery, their first follow-up question is typically always, so like for planetary defense or like to stop impacts, which asteroid science is so much more than just that. But the fact that that's where kind of the public consciousness sits, I think is great. And that just shows, and it kind of backs up what that Pew poll showed, that that people really do care about this, because, it could theoretically be an existential crisis. So I think from my standpoint, just communicating about it, talking to people about it, showing interest in it, and if it is something that interests you, reach out to us, sign up, look at the Asteroid Institute's website, see kind of the tooling that you can explore with. There's also Asteroid Day, which is a kind of a public outreach and awareness day that's on 30th of June every year, that coincides with the Tunguska impact in 1908. That was actually founded by our parent organization, the B612 Foundation. And so just, I think from my standpoint, it's talking about issues and learning how to kind of come to a consensus and an understanding about how to mitigate these kinds of things.
Mm. And I was wondering too, in terms of involvement of other scientists, I guess maybe in terms of different scientific branches. I'm wondering, because one of the discussions that I had with Jody Martini was the type of asteroid can differ very much. So there's the rubble piles, just loose piles of rock versus the solid things. So I'm wondering, is getting other sort of branches of science in studying angles of the question like that also involved, or does even the THOR algorithm allow us even to take a look at what kind of composition the asteroid is?
Yeah, that's a great question, and absolutely, like the composition, what the asteroid is made out of is super important. And I do want to emphasize that we are a very small cog at the very beginning of a very large pipeline of science that happens. And so we try to find the asteroid. Before us are the people sitting at the telescope taking the actual observations. And then once an asteroid is discovered, there's an entire follow-up like effort that happens where people get more observations of it. They try to get observations of different filters to try to get understanding of the composition. Once you know the composition, that then kind of dictates what kind of mitigation strategy you might want to use. And then, as I said at the kind of beginning of the talk, the pipeline goes from discovery all the way down to actual disaster mitigation. And so there are people who model, what an impact would look like if it hit the ocean versus, a continental surface. There are people who model the effect of, say that you have a potential impact that's going to occur, and you see this kind of risk corridor mapped on the Earth. What is that going to do for the economics? There are space lawyers who figure out, what kind of mitigation strategies are appropriate given, all the treaties signed by the different countries. And at the end of the day, this is a pipeline that's also endorsed by the UN. So the UN is aware and has, I guess, mechanisms in place to kind of execute the planetary defense pipeline.
Mm-hmm. And in terms of communication with the public, I guess is, when I think back to, for example, the COVID pandemic, a lot of scientists were saying it's a real problem, but then a lot of pushback, and people say, well, it's not as bad as you say it is. And I guess with the probabilities of asteroid collisions being a calculated number, I'm wondering, is there a way to communicate to the public that it's not just something that they can wish away, that it's, the calculation of 3% chance of hitting Earth could change either way, but it's something to be taken seriously, I guess. And maybe that's a question for both of you in terms of how that kind of communication can go effectively to the public without getting dismissed. And I guess in terms of outreach from the B612 Foundation and Asteroid Institute, how can that message be transmitted clearly and involve a lot more people?
Kind of going back to 2024 Wire 4, right? There was an example of newly discovered object, had some risk. I think a lot of people were just seeing newspaper headlines. Oh, like at one point the risk was, I think it was above 4% or something. And there was an increase, and then it went down later. Again, with all of the new asteroid discoveries that are likely to happen over the next several years, it is very likely that we are going to have some other objects that kind of fit exactly into that category. Most of them likely will not have an impact. Maybe one will. But I think whenever you have something that is kind of there's a bit of complicated, involved modeling and science involved, and you're trying to communicate it out to the public, you do have to have tools to kind of reduce that messaging down such that people can actually absorb it without necessarily having to become experts themselves. And I think it was Ed Liu, who's the executive director of our organization, was saying, in some ways it's kind of like hurricane maps, where people are now kind of familiar with the idea of something probabilistic, where if there's a hurricane and the meteorologists are showing people, here's like that cone shape that the hurricane might be in over the next 4 or 5 days or something. And they see that cone kind of getting bigger as time goes on, because people they've gotten used to those visualizations, and they kind of understand the more time goes on, the less certain we can be about some aspect of that. So I think similarly, not exactly the same, but I think similarly, as more of these objects come out and, government agencies put out their impact probabilities, and academic institutions who take these detections also confirm those, and organizations like us who are, vetting and are in agreement with these governmental organizations about what the odds are, they will kind of see this messaging, and people will start to develop a bit of a mental model for this, right? So I think after, say, the second or third one of these that is likely to happen over the next few years, people will say, oh, okay, this is the part where the impact probability is increasing, right? And then as it gets more refined, it's either going to drop to 0 or shoot up to 100% at some point, right? So I think that, in combination with things like, there are visualization tools, there are other people that are, building these kinds of tools. And I think people will just start to get used to seeing things like, oh, here's the risk corridor of the impact on the Earth. And it might be, sure, there's kind of a scary aspect to it. I think people should know that the most dangerous objects generally are easier to discover because they're bigger. And that means they're brighter in the sky. So we know already where more of the most dangerous, biggest objects are. That doesn't not say we know where all of them are. And ones that still pose significant risks, we are getting better and better at at tracking. And yes, it's a very open, coordinated process that happens, in the both at the telescopes and at academic institutions and at governments and third, NGO organizations like ours.
Right, and the public has access, I think you mentioned earlier, to Atom.
Yep, that's right. The public has access to Atom. They can run and look at the impact data and really all the data, like all those observations that get submitted to those objects to the Minor Planet Center. Anyone can go fetch those. They can get them from us. They can get them directly from the Minor Planet Center. And if they're so willing and inclined, they can learn how to do the orbit fitting and propagate that orbit through time and verify it. So they strictly don't have to rely on just other parties telling them what's going to happen. They can vet it themselves.
Right, and I should mention that the B612 Foundation is a U.S. charity, so U.S. contributors can get a charitable deduction for it. Also I would mention, because I've listened to a few things that Rusty Schweikert has said, that I think there's great inspiration from listening to him and his perspective. He was the first astronaut to walk in space, I think. Was that back in, I can't remember the year now, 65, something like that. But his perspective, I think, is very interesting. And I think his passion that comes through in his talking about defending Earth, I think is very helpful for people to understand. So I would encourage people to listen to what Rusty has to say. And maybe we could end up our discussion here by just talking about what's lying ahead for both of you in terms of what the focus of your work is going to be, say, in the next year, and where you think things are going to head from here to, say, a year from now. Is there going to be a major change in some particular aspect of the work that you're doing, or rate of discovery, or just your thoughts generally about how things are going to evolve in the next year?
Yeah, maybe I can start off with a Thor specific roadmap, and then Alec can chime in on organizational level. So one of the main priorities we currently have is to make Thor really good at finding NEOs, and particularly those ones that might hit the Earth one day. And as we said earlier, the challenges are really just compute. It requires a lot of compute power to be able to make Thor very efficient and really good at discovering NEOs. And so we are working on a whole bunch of different kind of strategies to make Thor as fast as possible and to make it a really powerful kind of NEO discovery algorithm. And so I think in the next year, if everything goes well, we'll see a new version of Thor that comes out. And ideally, that version of Thor will be running daily on the observations that get submitted from all the different telescopes, but also from Vera C Observatory. And maybe a year from now, we'll have some new NEOs that we have been able to help discover and can showcase that we continue to contribute to this field.
Yeah, that sounds exciting. A new version of Thor that runs data daily. So yeah, good luck with that. And again, if the public supports efforts like this, either financially or just in terms of moral support, I think that's critical. Alec, your view of where things are headed in the next year, and where you would like things to be in a year from now?
Yeah. So obviously, not just what Joachim said. If we want to do what Joachim described, and we want to get it set up in, I would think of it as, a fully production system, right? So we want that running against the soon to be very large amounts of data coming from Rubin Observatory in conjunction with all of our other data sets. And we have our site set pretty broadly in terms of asteroid discovery, but also in terms of we've been expanding some of our tools to go into areas such as characterization. We've been looking at things like rotation rates and light curves, which is something we had not previously been developing for. And I guess I would say we think we can really increase the amount of available tools on helping both astronomers, the public, mission planners, others in terms of the available data on all of the objects out there and just being able to make use of it all. So this obviously it's kind of a necessary step for the planetary defense, but it also kind of tracks to interest in the solar system as a whole. So we have kind of grand ambitions as far as that goes, and we'll just see as far as we can get with our limited team and our limited time.
Yeah, well, that's great. I mean, things have to start somewhere, and you've certainly, I think things have gone a long way. I think since we last spoke 2.5 years ago, and so it's great to hear the update and where things are headed. And we wish you all of the best luck with it. And certainly we want to follow the story and make sure that people understand the importance of the mission and contribute in whatever way that they can to it. So I wanted to thank you both for very informative discussion. I think this has been really interesting way of looking at something, as I said, that doesn't really hit the daily headlines, but is still extremely important. And so it's good to hear about good work and good developments happening instead of the daily horrible headlines. And so we wish you more success with the good work that you're doing, and we look forward to following up with you very soon and to hear how things are progressing. So thank you both, Alec and Joachim. It's been great talking to you.
Thanks
Thank
for
you so
having
much.
us.
Yeah.